Right, let's have a look at part 2 then. So this is slightly more complicated. Again, I'm thinking about the OCR chemistry A spec here. So last time in part 1 I was looking at, well, what if you've got an unknown mole of reducing agent in your flask and you want to find out how many moles of reducing agent are in there, and that was relatively straightforward. You titrate with potassium permanganate or manganate 7 ions. The complication there was that it needs to be acidified, and more importantly is that each mole of potassium permanganate or each manganate 7 ion can actually deal with 5 electrons. Okay, so sometimes the balancing doesn't work out so well there. Now this other kind of titration is more complicated, but fortunately it is a little bit simpler mathematically most of the time. So let's flip the problem around. What if in my conical flask I've got unknown moles of an oxidizing agent? I'm not quite sure how many moles of oxidizing agent I've got there. And unfortunately, yeah, the sad problem is there just isn't a convenient reducing agent to put in the burette. You know, potassium permanganate was great for the burette. It was self-indicating. It was its own catalyst. Okay, there isn't a convenient reducing agent we can put in the burette to titrate against the oxidizing agent in the flask. So let's think about a different problem. Okay, and just bear with me on this one. We'll see where we're going. What if in the flask you had some iodine solution? Okay, what if you wanted to know how many moles of iodine were in there? And the way you could figure that out is, well, the reason I'm going to use iodine is because it's got an indicator that's fantastic. It's starch. Now you might remember in biology, starch and iodine give you this really dark blue-black complex. Okay, that's our indicator, because if we've got iodine in the flask at the bottom and we throw some starch solution in as well, it'll be really, really dark coloured. And once the iodine has been changed in some way, well, we're going to turn it to iodide ions, it'll lose its colour. So we start with an unknown amount of iodine in the flask and some starch. Okay, and as we add the thiosulfate ions, the iodine changes to iodide ions and we'll lose the dark blue colour. Okay, so that means we've got a way to find out how much iodine, and we're using thiosulfate, by the way, because the electrochemistry works quite nicely. Okay, right, now what happens in the flask is the aqueous iodine reacts with, okay, so we've got some ratio going on here. We've got 2 thiosulfate ions needed to react with 1 mole of iodine. So that might be a complication. Okay, because 1 mole of thiosulfate from the burette, it's only actually going to reduce half a mole of iodine. The basic principles of titration still apply, though. It's just in this one, our little n figure is a half. So the number of moles of iodine that you had in the flask that you didn't know to start with will just be half the number of moles you had from the burette. But our original problem was if we had oxidizing agent in the flask, not iodine. Okay, I've got some oxidizing agent dissolved in that flask and I want to know how many moles of it there are. So what we're going to do is this. We're going to use the oxidizing agent to oxidize the iodide ions to iodine. So we're going to mix it with some potassium iodide, okay, and that will oxidize the iodide ions to iodine. Then we're going to titrate that with thiosulfate to find how much iodine we've made, and then from the amount of iodine we're going to work backwards how much oxidizing agent we must have started with. Okay, so let's have a look at an example. Now, copper, okay, I've done one of these questions where I've cut out the unnecessary words and the backstory. The backstory could be something like we've got a sample of brass and they dissolve it in nitric acid, and that will give you an unknown number or an unknown amount of copper ions. Okay, and that's where we're going to start from. We've got a flask, we've got copper 2 ions in it. Now copper 2 is quite a good oxidizing agent, okay, because what it will do, it's quite happily take an electron, and when you do the transition metals chapter this will make more sense. Copper will flip from copper 2 to copper 1 very readily. Now the reason why that's going to happen is because we've added iodide ions. So we use the thing we're interested in to actually change the iodide ions to iodine. Now you can see I need to do some clever stuff here to balance that up. I'm going to need 2 of those to make an iodine. So I'm going to generate 2 electrons, and then because I've got 2 electrons on this line here, I'm going to have to double up the top to give me 2 electrons being used. Okay, so if I double everything up on the top, add those together, we should get the reaction that kicks this thing off. And again, I'm not putting the state symbols in just because I'm working on a writing screen that doesn't give me a lot of fine control on my writing. Okay, T plus, and there's an iodine, and there's our 2 electrons, and the electrons cancel because they're the same number, so that's useful. Okay, so what we've established from that is the first part, the reaction we did before we started the titration, is that 2 moles of copper in the flask produced 1 mole of iodine. Yeah, so 2 moles of copper that we started with as the unknown at the very beginning, after our reaction will have made 1 mole of iodine. Okay, so our copper is 2 times the iodine. Okay, and we'll come back to that later when we need it. Right, now onto the titration part. So we've got to figure out how much iodine is now in the flask. So we titrate it, and of course with titrations, I did say the first thing to do is work out how many moles you added. Okay, so we've got 0.01 times 28.0 divided by 1000. Okay, so that's going to be the number of moles of sodium thiosulfate we've added. And I've managed to, there we go, put my calculator somewhere silly. Here we go. Alright, so 0.01 times 28 divided by 1000. Okay, so that's 2.8 times 10 to the negative 4. Okay, and that's, just remind ourselves, that's how many moles of thiosulfate were added. Now we need to look at the blue equation up at the top there, because we're going to use that because this is the actual titration equation here. And when we look at this one, you can see that, as it turns out, you need 2 moles of thiosulfate to react with 1 mole in the flask. So what that tells us is that the iodine is going to be half the number of thiosulfate moles. Okay, because the thiosulfate, you actually need 2 of them to react with 1 mole of iodine. So the iodine is going to be half of that number, which is 1.4 times 10 to the negative 4 moles of iodine. So we've worked out how much iodine was in the flask at the start of the story. Okay, now we go back a step to this line here, where we worked out the amount of copper that made that iodine is actually twice the amount of iodine made. Okay, so the copper is twice the amount of iodine. Okay, because what have we got here? It takes 2 coppers to make 1 iodine. So we end up doubling the amount of iodine. So we end up back where we started, and that's the mathematical thing that's rather elegant about this, is because the titration, you halve the ratio, but the actual initial reaction almost always doubles it. You tend to end up back where you started from. In other words, the number of unknown moles of the species you're interested in, which is copper in this problem, often turns out to be the number of moles you added from the burette anyway. So this is that kind of question where if you get really stuck with your ratios, assuming it's 1-to-1 pays off. Okay, so we've got right back to the beginning here. We've worked out how many moles of copper ions were in the flask, and quite often what they're interested in is what the mass of that will be. So that will be 63.5, which is the relative mass of copper, times the number of moles of copper. Okay, so I'm going to times that by 63.5, and that will be 0.0178 grams. Now that's just the core of the problem. That's the reaction where you use iodide, or sorry, we use the oxidizing agent you're interested in to produce iodine, and then you titrate. Those questions are often buried in more detail. I've seen quite a few where the copper is in brass, so there's to dissolve a piece of brass and you're trying to work out the percentage of copper in something. Occasionally they're sort of have a solution where you've got 250 centimeters cubed and they titrate 1/10 of it, so you've only found out what 1/10 of the quantity is. But as with all titrations, the complicated ones, if you start at the bottom of the story and work backwards, you should be able to get to the end. Now I did a little bit of thinking about how these questions work out, as in how safe is it assuming the ratio is always 1-to-1, and thinking back, well, The first issue is that when you go that you're not going to get a ratio that gets smaller, because each mole of iodide has only got one electron to give. You could get one where the ratio goes the other way, so you could get one where the ratio doubles. In other words, you actually need 2 moles of iodide to react with 1 mole of the oxidizing agent that you're interested in. I haven't seen many questions like that in OCR, but I suppose it could happen. But the bottom line is, with this one, most of the time you can assume that the ratio just stays the same all the way through, because you halve it and then double it and it cancels out. You can pick it out on question by question basis, so hopefully that's going to help you with these difficult problems. Remember, if it's a great big long titration, a sort of 5-6 mark one, start at the end of the story when you get told how much was used and what the concentration was, and work back up the page.